12 grams could be expressed as a picogram. Picogram. Yeah. So that's not one that you're going to be memorizing, but you know where to go for the lists. A nanometer, how many meters is that? 10 to the minus 9. Good. 10 to the minus 9. 10 to the 6 grams? Megagram. I think that's the name of a superhero, right? A microliter? 10 to the what? Minus 6 liters. Hertz, HZ. 10 to the 9th. Gigahertz. Isn't that how they identify the speed of your computer, right? How fast the RAM rewrites? Okay, good. Something good. All right. Let's move along. So these are some things that you are familiar with, but probably not familiar enough with the specifics. I shouldn't say not familiar enough. You're not familiar enough to just start spewing out the values. But I'm not interested in that. Ever since Google came out, we don't need to memorize all these tidbits, right? If it's important, you'll use it so much that you won't memorize it. You'll just know it because you use it so much, right? If it's not important, then you just keep using your phone. But we know that there's these relationships, right? An inch is not a centimeter, and so forth. So some common measurements. This is my favorite. 3 liters of Coke. These are some common glassware units. Yeah, I don't know his name. Is that what you're going to ask? No. What was you guys?
What's an SI unit?
Okay, SI unit. Did we? Oh, for this one here?
Yeah.
So back here, remember when we said that there were some standard units? So what they're doing is they're saying, whenever you talk about length, the standard unit is a meter. Whenever you talk about mass, the standard unit is a kilogram. All right, and you have this list. And it makes them feel super important. And it's great. And whenever you want to be official, you can go to this list and use it. But my experience is, you just go to a lab and find out what they're doing, and you keep those standards. So the place where I worked over this last year, they still used inches. Bunch of engineers, and they used inches. And you know, we're dealing with really, really small things. But they would just say, oh, 6.5 thousandths of an inch. Okay. Now, we could call it a micrometer if we wanted to, but no, we'll call it a thousandth of an inch. So we were just always talking in inches and stuff like that. And so it didn't do any good for me to say, that's not a standard unit. Let's get this place shaped up, right? So you just have to become familiar with what it is. But there is a list of standard units out there. Okay, let's see. This one is kind of tricky, for me at least, and I don't always remember it. A common football player, 220 pounds, that's normal, maybe, I don't know, 100 kilograms. That seems to be a helpful one, because if you come from a place outside of the United States, you know how much you weigh in kilograms. If you come from the United States, you don't know how much you weigh in kilograms, right? So that's one that's kind of helpful. This one is also interesting. If I take 1 cubic centimeter of water, that becomes the definition of a milliliter. All right? Or not just of water, of any substance. A cubic centimeter of whatever it is a milliliter of that. So we've taken centimeters, a length, and we've turned it into what kind of a unit? What's that? What's milliliters? Is that, what kind of measurement is that? Is that mass? Is that length? Milliliters. Volume, right? And yes, 3 lengths are required to identify what the volume is. But we transfer from cubic centimeters to milliliters. There's another example right there, right? The SI unit for volume is the liter. So you would maybe expect people to use milliliters. But what do they use in the medical world? What is the unit that you use in the medical world? If you're planning on being a doctor or a nurse, you have to be ready to use cc's. You know what cc stands for? Cubic centimeters. How ridiculous is that? I mean, instead of, there is something called a milliliter, and you know, it's the same thing as a cc, but no. And on the side of the containers of the stuff, it says milliliters. It's in milliliters, but they still use cc's to refer to milliliters. So, you know, traditions get in things and they get stuff there. We had our conversation about Kelvin and Celsius, right? What was the name of the other gentleman who was good at blowing glass? Fahrenheit. Very good. All right, and this is our example of one of our experiments that showed that there is such thing as an absolute zero, right? If you take gases and cool them down, their volume shrinks. So it would come to a point where the volume of your system would begin to be negative, and people realize that can't be true. So, have you guys heard of Bose-Einstein condensates? So there's solid, liquid, and gas. And if you get gas really hot, it moves the gas around faster and faster. But if you get a solid really cold, it actually becomes something different, which is called a Bose-Einstein condensate. It has this weird name based out of the people who discovered it, because we never interacted with it to any significant extent, right? Only in the last 20 years have we realized how to make them. They had hypothesized way back when that if you got something really, really still or really, really cold, you make this new type of matter that has bizarre properties. And we're just barely getting to the point where we can start measuring some of these properties. Use, I don't know if use they could ever be for anything, because I mean, you're talking about systems that are super, super duper cold, and any small amount of energy added to them would completely change them, right? Another part of the theory was that we can never reach absolute zero or stillness. And there's beautiful documentaries called The Race to Absolute Zero on YouTube. If you're ever wondering if this is a 4-star, 3-star movie, The Race for Absolute Zero is a good one. It's really good. Right? Very good. Anyway, we talked about that. There's an equation for converting temperature from Kelvin to Celsius. There's an equation for Fahrenheit to Celsius. I found the easiest way is to just say, what's the temperature, what's 25 degrees Celsius in Fahrenheit? That's much easier than anything I've ever found. So, if you want to try that, you can try that as well. Now, uncertainties in measurement. Did you know that I'm a good golfer? I golf frequently. Yes, recently. So, when I hit the golf ball, I hit it on average right in the hole. Sometimes I hit it longer, sometimes I hit it shorter. But my average shot, I've determined, is always right in the hole. Does that make sense? I actually have never hit the ball in the hole, but I'm always right on average right in the hole. Does that make sense? So that's an example of there needing to be another way to describe how good of a golfer I am. True? Because if I told everybody I'm a good golfer, on average I hit it always right in the hole, people would say, oh wow, that is a good golfer. Right? But the average doesn't represent the reality of things, right? So we have words like accuracy and precision. Accuracy and precision. If I'm precise, then that means I always hit the ball in the same place, right? But to be accurate, I'll have to hit them all to the same place and in the hole. That's the sign of accuracy. Not just hitting them all in the same place, but hitting them all in the right place. Okay? And every measurement has a degree of uncertainty. And these uncertainties we call, or identifying this uncertainty, we use what we call significant digits or significant figures. Okay? Let's say I want to go sell my ring. I'm going to take my ring to the pawn shop and I'm going to sell it. And they say, we'll give you this much for every gram. I go, great. And they put it on the scale, and they say, okay, looks like you got 21 grams here, we'll give you money for 21 grams. This is my grandma's wedding ring. I'm really sad to let it go. What would you do if they told you they're going to pay you for 21 grams? What's that? Yeah, it's a little bit more. I see there's a little bit more. No, the boss says I can only pay for what I can tell for sure. Right? So what do you do then? How hungry you are? You go somewhere else, you get a better deal, right? Somewhere where they have a better scale. And on that better scale, you get increased accuracy. And now you can see that it's actually what? 21 point. You and your neighbor did give me a number that would fit this, and then give me a number that would fit that one. Okay? What number does it look like? Just talk to your neighbor really quick. Get a number for me. I'll write them down for you. You ready? What numbers does it look like? What numbers would work? The one on the left? 21? 21.2? On the left, could this be a possible number on the left? How about this one? Where am I getting these numbers from? I'm making them up, right? Is there any way I can tell down there? Could they be right? They could be right, but that doesn't help. That doesn't help us. It doesn't help to just make up some numbers that could be right. We want to know, based on the measurements, only the numbers that we are confident in. We're definitely confident in the 21, right? And for significant figures, when we're making measurements, we allow ourselves one, what would we call that number? It's an estimation, right? An estimate? Because we don't have the information from the left side. So, that tells us that there's 1, 2, 3 significant digits. I can't just start putting in the numbers, right? On the right, though, how many significant digits can I get? What value does it look like on the right there? 21.3? Can we see it for sure? We can see the 3 for sure. And then we get to estimate 1. 1. And you know, it might not be 1. I don't know. We get to estimate. So we see that we have an increased significant figure number 4 here, 4 significant figures here, as opposed to the 3 over here. Okay? Good. So that's how we identify significant figures when you're making measurements. Some numbers, like a dozen, are exact numbers. They're definitions. They don't have to be limited to the number of significant figures. All right? Exact numbers. So these are the rules for significant digits. Any number that's not 0 has that many significant, or is a significant digit. So here's 21.3. We have 3 significant digits. All these are numbers, and so all of them are significant. If there's a 0 in between real number or significant numbers, then they're also significant. So essentially, if somebody could look at their scale and see that it says 2.0056, based on where the value was, there was something there that allowed them to see this 0, 0, right? Because they could see this, and they could see this, therefore they would be able to see those numbers in between. So all those numbers would be significant. In this sort of a scenario, if it just says 2, 0, or 3, 0, 0, we don't know whether or not these zeros were actually significant numbers. So that would only represent 1 significant digit. If we wanted to help people realize that, hey, these are significant digits, I could put a a decimal place there. Okay? Zeros to the left of numbers. We don't know that there's any ability to actually read those values, so there's no reason to think that those are significant. Okay? Make any sense? Maybe you guys got to study this a little bit before you came, right? How many significant digits do we have here then?
3.
3. Hooray. How about here?
3.
1, 2. Oh, 2, 3.
1, 2, 3, or 4. Probably one of those. Why don't you talk to your neighbor just for a second, see what they say. They might know.
3.
Okay, so then the answer is definitely this one, right?
Yes.
Okay. What about that 0 there? Is that significant?
No.
How do we know? Why did the person write it there? The only way they could write it there is if it was significant, right? You wouldn't be writing anything beyond that decimal place if it wasn't significant, right? So that decimal shows us that these two zeros are for sure significant, and the fact that there's actually a value written there shows us that that is the estimate. Okay, so we got 4 significant digits. How about this one? 1. 1 significant digit. 3 significant digits. Any questions with that one? 3 significant digits? Okay.
Well, I have a question.
Yeah.
How it's 3.
Oh, why is it 3? Okay, good question. So, this 0 over here, right? We don't have any values enough of whatever it is we're measuring to actually get any values there, so there can't be something significant. Whereas these zeros down here, apparently I could tell that they were zeros, and that's where they were written. Right? So the 5 is significant, and the zeros are significant as well. So let's look at a number like this. 1.1 millimeters. 1.1 millimeters. How many meters is that? How many meters is 1.1 millimeters? How many significant digits are here? 2. 2 significant digits. 2 sig figs. So, if we're converting this to millimeters, what does the decimal place have to do? Move over how many times? 3. Because there's how many millimeters in a meter? 1,000, right? 3 zeros. So is it going to go this way, to the right, or to the left? To the left. So 0.0011 meters, right? And so this can't have increased the number of significant figures. I can't increase the number of significant figures just simply by calling something else. So this still has 2 sig figs. And that's one way that you can help yourself remember whether or not those zeros in front are significant. How about in terms of micrometers? How many micrometers are in 1.1 millimeter? This time we move the decimal place which way? To the right. How many? 3. 1, 1, 0, 0. How many significant figures are here? Still has to be 2, right? All right, so that little exercise right there can help you remember how to identify how many significant figures there are, right? Something like that compared to larger or smaller than it, you know that there has to be the same number of significant figures. Okay, good job. We'll meet again on Monday. Okay, see you later.